Now we're actually going to start talking about some encryption. I edited this slide or the next batch, but fundamentals of it. We have a message. We have some sort of sender, receiver, and some medium to get it there. I could be sending it to Scott. I would be the sender. He would be the receiver. We could be sending it through the internet or through the airwaves or through whatever. That could be the medium. Plain text is always signified by a P. Ciphertext is by a C. So far, so good? Okay. All right. We could have an intruder. They could interrupt. They could intercept. They could modify. They could fabricate. So a lot of stuff could happen to our message. Okay. So far, so good? You with me? All right. We have cryptography. It says using encryption to conceal plain text. Okay. We have cryptanalysis, which is unauthorized code breaking. These are just different terms. And yes, some of them are on the test. And cryptology is cryptography and cryptanalysis. Now we're analyzing it and breaking it. Okay? Just some terms. Okay? Breakable encryption says analysts can determine the algorithm given enough time. So do you agree with enough time and enough data we can figure out how you did it? Mm-hmm. Yeah. That's pretty much it. Theoretically breakable says it's practically unbreakable. It's kind of like AES, 149 trillion years. I'm pretty sure no one ever actually saw how long it took and wrote down the time. They didn't start the stopwatch. Work on it for 149 trillion years to determine that. But it's also like, you ever see when you buy something like your keyboard will last for 1.2 years? You ever see those systems actually test them? They have a machine that goes. It just hits non-stop. It's like, wow, it's pretty crazy stuff. We also have brute force attacks. That's trying everything. It's like an ATM. What's the combination of numbers for an ATM? Not very much. It's only 4 digits. Okay. Ingenious attacks. We'll see more about that. But someone just comes up with it. Oh, I guessed it. Or I figured it out. Did you ever have somebody you could just guess it? Yeah, that could be an ingenious attack. Okay. Now we also have something called the estimate of breakability based on current technology. Now that's the thing that changes. And there's something called Moore's Law. It says the number of transistors on a chip double every 2 years. Basically the speed is doubling is what we're saying. So computers are getting faster every 2 years. So what does that mean? You buy a nice computer today, but wait a minute. Next month it'll be quicker. So when do you buy one?
It means my Android phone is faster than my first computer.
Yeah, that's really is. So, you really got to decide, since they're increasing the speed so quickly, I have a 65-inch LCD TV at home. Beautiful TV. I absolutely love it. But it's LCD. That's not the new technology. So I want an LED now.
What's that new one?
OLED. Yeah, it's just... Whenever you buy something, there's always something new.
Banging olds to $40,000.
And what's in these movies? See Mercury Rising, Bruce Willis? It's where this kid could basically, he was an autistic kid, could basically just solve stuff.
Anything with numbers.
Right. Or like Rain Man. Virginia, my wife, my stepson David, he has Asperger's syndrome. I don't know what the hell it is, but he has it. But when it comes to numbers, he's really good. And what kind of freaks, what's bad is he'll sit in math class and just write down the answers to the problems. Well, when he was in school in Norman, they were fine with that because they knew him. He moved to Kyle Albert. Guess what you think happened? Like, oh, hell no, you need to show your work. And he goes, I don't do any work. I just write the number down, the answer. But that was the biggest issue. But I tried to tell him, you need to show your work because you're not always going to just know the answer. Even though majority of the time he's right because he's really good with math. But, it's like, how did Raymond do that stuff?
They have different formulas of doing it, though.
Yeah, they do have weird ways of doing it. Okay. Now, basic encryption. We have key-based ciphers. So it provides more security than keyless. In other words, the encryption that has a key is better than one that doesn't have a key. Easy enough. Okay. And the way you would read this is the encryption key. In other words, the key used for encryption. The decryption key, the key used for decryption. Okay. So far, so good. So we could take our plain text, encrypt it with our encryption key, makes our ciphertext. Everybody see that? So C equals P in braces KE means plain text encrypted with an encryption key equals ciphertext. So the next line down, so if we took our ciphertext, encrypted it with the decryption key, that becomes our plaintext. But that's also equal to our plaintext encrypted with an encryption key and encrypted with a decryption key, which is also equal to our plaintext. Everybody see that? So it's just another way of showing it. It's the same thing. Okay. We also have symmetric and asymmetric. Very important. Now, it's probably on all three tests, but you should know it at that point. Symmetric, same key. The encryption key and decryption key are the same. Symmetric, same. S, same. Easy enough. Okay. Asymmetric, they're different. The encryption key and decryption key are different. Which one's faster? What do you think?
Symmetric.
Symmetric is much faster. AES is symmetric. But there's a problem with it. Anyone know what the problem is? We haven't even covered it. Anybody know what the problem might be? Right, you figure out one at the key management issue. You know, me and Josh are transferring data across the country. Whoops, Josh's password got compromised. Guess what? So did mine. Because we use the same key. Whereas asymmetric, they got Josh's password. They ain't got mine.
Josh is screwed.
That's it. Okay. So we'll see a whole bunch more about that. Okay. Symmetric. So symmetric is an encryption algorithm where the same key is used for both encryption and decryption. The key must be kept secret, and it must be shared with the sender and recipient. We're actually going to talk about Diffie-Hellman later on, where we can learn how to transfer that key over the internet, but no one's seeing it.
Say that again?
We're going to be learning something called Diffie-Hellman key exchange protocol.
Okay. Yeah.
We're going to show you how me and Josh can share a key over the internet.
So now you've taken the U.S. Postal Service's job totally away.
Exactly. Now they're gone. They're going to be gone soon anyway. Okay, so symmetric, same key. S, same. You got that? Okay, so symmetric, also known as private key or secret key encryption. Okay. We want to keep them both private, both secret, same each. Okay. One key per channel. So me and Josh are talking. How many keys do we need? Just one. Me and Jimmy are talking. One.
Another one.
Okay. 38. Get out of here. Okay. Now, here's how many keys we see. N users. Okay. So if we have, let's say, in my example there, I got 4 users. Okay. So 4 times 4 minus 1 divided by 2. So 4 times 4 minus 1 divided by 2. So it's 12. 4 minus 1 is 3. This is the major algebra. This is why you took algebra. 4 times 3 is 12. Divided by 2 is 6. Now if you were to write A, B, C, D and draw every connecting line you can between them, there's only 6 keys needed. So for each person to be able to talk to each other person with a different key, I don't want the same key to work for Jimmy and for Josh. That's the maximum. Again, skip the green line. That's not real. Okay? So, we have authentication as long as the key is kept secret. But key distribution is a problem. I need to get him the key, and we're going to talk more about that later on. Management is always an issue. Okay? The storing, the safeguarding, the transporting, the activating, all that stuff's important. Okay? Are we okay with symmetric encryption? We haven't learned about the different algorithms yet. We're just learning about it in general. Okay? So we have 8 users. You need to know this, okay? 100% positively on the test. Guaranteed is on there. Okay, and when I give you the test with this kind of question, I kind of screw up the algorithm a little bit. And I know how you're going to screw it up. So I make sure that if you screw it up, that answer's on there too. So it makes it much harder to guess it. So I'll do like n times n divided by 2, in case you forgot the minus 1.
Why?
Just to see if you really do the correct answer. Okay, so 8 users. So n is 8. 8 times 8 minus 1. So 8 times 7 divided by 2 is 28 keys. I'd draw that one out, but that'd be like some funky stuff. 56 is 8 times 7.
I know. Is that the channels?
Actually, there's only 28 channels. Yeah, if we picked 8 users in this room, For each one of us to be able to talk to each other person in this room, we would need a total of 28 keys or channels. All right, asymmetric. Now, public key encryption. We're going to learn about PGP later on. Okay? The encryption key and decryption key are different. Okay? This is also, well, yeah, public key. Just go with that one for now. Okay? 2 keys per user. I now have a private key and a public key. Okay? If we have n number of users, it's 2 times n. Okay? So, 4 users is 4 times 2 is 8. That's it. So 4 users here, 4 times 2 is 8, total of 8 keys needed. A little bit easier. Okay. Authentication now, as long as the private key is kept secret. My public key, do I need to keep that secret? No. I want that to be public. It's like PGP. If I want to send you guys something, encrypted with a PGP, I take my public key and tell the entire world about it. Then I encrypt the message with my private key, because I'm the only one who has that, then anybody in the world can decrypt the message now, because this key is public. So what the heck good did that do me? They don't know the private key, but still, anybody can decrypt it. So why did I even bother?
Because you can encrypt it with their public key.
Well, even if we don't go that part, what did we gain by doing that?
Oh, they know it's you.
They know it's me. Who's the only one in the world that could have encrypted something that would have matched that public key? That'd be me. So anybody in the world can open it, but they would know, oh, that came from Ken Dewey. It's a digital signature. I know who signed it. That's pretty much what it is. Okay. Now, what Roy was talking about, what if I'm making something, and we use Carol now for an example. Carol has a public key and a private key as well. She posts her public key on the web. I post my public key on the web. I'm sending Carol something. I encrypt it with my private key. Actually, I sign it. Well, I'll just say encrypt. I encrypt it with my private key and her public key. So I encrypted it twice. My private key, her public key. She's going to receive it. She's the only one who can decrypt it because it was with her public key. And she can tell it came from me because it was done with my private key. So we'll see more about that. We actually do some exercises in that. Okay. All right, basic cipher types. We have substitution ciphers. Could just replace characters. We have transposition ciphers. We don't do too much with these, but we'll see a little bit about those. We could scramble them, move them around. Substitution. The Caesar cipher made by Caesar. Yay. Okay, what he does is he shifted it by 3 characters. You have your first assignment using this. And I did record about how the assignment worked, but there's also a practice assignment up there, so you can walk and see how it works and see what the answer is. So you can make sure you know how it's done. Okay? I think it's for this one. Maybe it's for the second one. I don't know. But it says something they just shifted by 3. So A became D, B became E, and C becomes F. Okay? So you take your plain text, shift it over by 3, and that's when you get your cipher text. That's the Caesar cipher. Might be handy to know how to do that. Okay, so we shift 3 letters to the right. Return to Rome becomes this thing. Yeah, that one. And we run it backwards, and then we're good. Okay.
I'll bet Si could read it.
Yeah, probably. Okay, he can do everything. He was in charge of this back in Nam. Okay, monoalphabetic ciphers. We have a key-based cipher, which now is encrypting something, but we're using a key as well. We'll go over a whole bunch more about that. Okay. We have substitution where stuff could just be mixed up as well, just a bunch of different ways. Now, I mentioned here something called a single alphabet. Okay. We're going to be playing more with that. We're actually going to work with some of the multiple alphabets, but the Caesar cipher is a single alphabet. Okay. Okay, how do we break them? Well, we could do something called frequency distribution. What's the most common letter in the English alphabet? It's an E. So if I was to look at the number of E's, the number of A's, the number of Z's, the number of everything, and calculate, using a formula, calculate a number, English, which is called the index of coincidence, which we cover next class, Barry. Index of coincidence is 0.0667. So I can take plain text, run it through the index of coincidence algorithm, and find out what language it's in. Would that be handy? Oh, most definitely. Most definitely. Okay? Computers make code breaking trivial because they can do this stuff a lot faster than I can. We can also do something called flattened frequency distribution. So if we know E is the most popular letter in the English alphabet, so what if I made it so every letter was equal frequency? Would you be able to tell it's English? No. So that's one way. We can use polyalphabetic or multiple alphabet ciphers for that. We'll see how all that works as well. Okay, here's the frequency of the letters. You'll see E is the most. And then I guess T. Anyone ever remember Wheel of Fortune? N, L, S, T, R, and E. Remember when they didn't give them the letters originally?
Yeah.
And some of you, like Roy, ain't old enough. But they actually had to pick those letters. Now don't they automatically get those, don't they? It's not even fair. Okay. So the index of coincidence is a statistical measure of text which distinguishes text encrypted with a substitution cipher from plain text. Okay? There's a book about it. Okay? It's known as the single most important publication in cryptography.
Why?
Because that's when they first started using this stuff. Like, wow. And it's really kind of cool. It says, index of coincidence. Here's how it works. Again, we'll cover it more next time. It's defined as to be the probability that two randomly selected letters will be identical. So imagine taking two hats, each with 26 letters, each with A through Z in them. So I have two hats, each with A through Z. The chance of pulling an A out of a hat is 1 out of 26. Do you agree with that?
Yes.
Okay. So the chance of pulling a B would be 1 out of 26 as well, because as long as I put the A back in there.
Right.
Okay. All right. So what if I had two hats? The probability of pulling an A simultaneously out of both hats is 1 out of 26 out of one hat, 1 out of 26 out of the second hat. Okay? And multiplying them. Okay? Now, the chance of drawing any pair of letters will be 26, because there's 26 of them, times 1 over 26 times 1 over 26, which equals 1 over 26, which equals 0.0385. And we're going to do math and show how this actually works. But it says the index of coincidence of an evenly distributed alphabet is 0.0385. Because remember, we're not talking about one has more than the other. We know an E has more. But in this here, they're an evenly distributed set of numbers. There's 1A, 1B, 1C, 1D, 1E. So if I asked you what was the index of coincidence of English, you would tell me 0.0667. Okay? Because remember, there's more E's, and more S's, and more N's, and very few Y's. So if I had a hat of English, that hat would not have one E. It would have a whole pile of E's, and maybe only one Y. Okay? But if I have an evenly distributed number of letters, in other words, 1A, 1B, 1C, 1D, 1E in each hat, it's 0.0385. Okay? And we do cover that some more. Okay? So suppose we fill the hats with 100 letters and have the number of each letter correspond to the average frequencies of the English language. For instance, now instead of 1A, 1B, 1C, we have 8 A's, 3 C's, 13 E's, so on and so forth. That's what we have in English. So now we're going to, instead of 1 over 26 times 1 over 20, so we have 100 letters total. We have 8 over 100, then we have the 3's over 100, then the 13's over 100, and that's where we get the 0.0667 from. That's how come it works for English. Okay? Now, every language has their own. English is 0.0667. Has anyone ever seen other languages? Like Russian and Spanish and how about Chinese? Oh no, I ain't going there. It's I take a cruise to Mexico or something. I stop in one using an internet cafe. The letters are always screwed up. You can't find the @ sign and stuff, and it's tough because they have different mappings. Because they have different letters. Okay, so the frequencies change. Okay, how is this useful? It says index of coincidence can be used to test if text is plain text or ciphertext. Okay, talk a little more about that later. Text encrypted with a substitution cipher would have an index of coincidence closer to 0.385, since the frequencies are more random. Okay, We talked about in English having 0.667. That's why computers just make it so easy to do. Okay, we're almost done with this. Actually, I think we are done. Okay, there's a lot of source stuff I'm going to give you through here. Again, you don't need to read them, but if you wanted more information about it, you can read about it. Okay, next time we're going to start polyalphabetic or multi-alphabetic ciphers. Now, your first assignment is due